Hi everyone. So we will be continuing with the definitions and properties of non-deterministic finite automata. We left off at multi-step extension of the transition map and what it means to for a non-deterministic finite automata to accept a language. So what we had said is that at length 1 strings, it basically means that delta hat AA is the union over all Q in A delta QA, where A is this length 1 string. And then we said that the NFA accepts X if delta hat Sx intersection F is non-empty. In other words, it accepts X if there exists a path starting at a start state, ending at a final state, and labeled by the input string X. The accepted language is the set of all strings where the NFA accepts set of all strings X where the NFA n accepts X. So let's look at a few more structural properties of this multi-step transition map delta hat. The first lemma says that for any X and Y of sigma star and a given subset A of given subset of states A of Q, delta hat A X Y is equal to delta hat of delta hat AX comma Y. So basically it is saying that no matter how I break up this input string, let's say XY, suppose the input string is XY, even if I break it up into following the paths labeled by X first and then following the paths labeled by Y, even then we will end up in the same set of states. The final endpoints will be the same set. So again, the usual strategy is to use induction, and we will be inducting on the length of Y. In the base case, Y is epsilon. Now let's look at the left hand side, LHS. LHS becomes delta hat AX X concatenated with epsilon. This basically is delta hat AX, and then this is delta hat of delta hat AX comma epsilon by definition. So if you think of the base case of the definition of delta hat, then this, let me use the pen, then this is the left hand side, this is the right hand side, and this is the left hand side. How? Because delta hat AX is basically a set of states. So that can be thought of if I'm at a set of states and I read an empty string, that is I do not get an input alphabet, then I stay in the same set of states. So delta hat of a set of states and epsilon will just be the set of states. So this is the left hand side of the definition and this is the right hand side of the definition. So the statement holds for the base case. Now let's look at the induction. In the induction hypothesis is that suppose it is true for all x and for all y of a up to a particular length. Now we are going to be looking at ya for some alphabet a in sigma. So now how do we do this? Let's look at the left hand side of the claimed statement, that is delta hat a xy. This is going to be equal to, by definition, union of q in delta hat axy delta of qa. Now let us zoom in on this delta hat of axy. Y is shorter in length than ya, and y is of the the length of y is at most that up to which we have defined the induction hypothesis on. So now we can apply induction hypothesis on this statement, the purple expression, and rewrite it as delta hat of delta hat ax comma y. This was the right hand side of the claimed statement. Okay, so then the expression got rewritten to union q belonging to delta hat of delta hat ax comma y delta of qa. Now, you can think of this as the right hand side of the inductive step of definition of delta hat, and this is the left hand side of the inductive step of the definition of delta hat. So the left hand side reads delta hat ax comma ya. Okay, and therefore now this is the left hand side of the claimed definition for the string ya, and this is the right hand side of the claimed definition for the string ya, and therefore we are done with the induction step, and therefore we are done with proving the lemma which says that no matter what x and y I get as input and any subset of states a, delta hat axy delta hat axy is equal to delta hat of delta hat ax comma y. So xy can be broken up in whatever way, but I will still be reaching the same set of end states. The next lemma is states that delta hat ax is equal to union over all p in a delta hat px, p being a singleton state. So basically it's saying that suppose I was starting from suppose my start state or let's say look at paths starting at a state inside A and labeled by X, and look at the end, look at all the states that are reachable by such paths. This is denoted by delta hat AX. All states reachable from A by paths labeled by X. This should be same as if I take union over all states in A and just look at all possible states reachable from that particular state by paths labeled by X. So graph theoretically it does make sense, right? What we are saying is look at the set of states in A, look at all paths going out of them labeled by X, and look at the set of end states. This is being denoted by delta hat AX, and you can also think of it as look at each state in A, look at all possible paths of labeled by X going out of it, look at the end states reachable, that is denoted by delta hat px, and now take the union over all such p. You can also formalize the argument by inducting on the length of x, and I want you to try this argument because it's good to have a rigorous practice of how to write definitions, how to write proofs, inductive proofs formally. So please try this on your own. I gave you a graph theoretic idea of why this should be true in the if we just look at the transition diagram, then intuitively it seems like it should be true. If I have all these paths coming out of A labeled by X, I can also think of them as a partition of paths coming out, partitioned according to the starting points which are in A. So now the question is, do NFAs have more power than DFAs? So one way is correct. A DFA can be thought of as an NFA. We can simply define the tuple. We can sort of define the DFA to be we can define an NFA structure corresponding to any DFA. Suppose the DFA was Q sigma small delta SF, small sf, then we can define an NFA Q sigma delta SF in this form. So basically, if there was one state If there was one start state, now I can write it as a set, as a singleton set. I keep the final states to be the same. The set of states is the same. Sigma is the same. And now, how do I define this capital delta in terms of small delta? So delta PA is now going to be the singleton state delta PA. So small delta PA was a single state, and now I just define it as a set, as a singleton set, and this will be good enough for us. So what this says is that if a set of strings is accepted by a DFA, then it is also accepted by an NFA. But the more important question is the other way around also true? So suppose there is an NFA N which is defined by the structure Qn sigma delta n Sn Fn, and suppose Ln is the set of strings accepted by n, can we construct a DFA that accepts Ln? So intuitively it seems like we should be capturing, basically we have to capture all possible paths. In the DFA, we should have one path labeled by X. Exactly one path labeled by X. So what we have to do is, we have multiple paths labeled by X in the NFA. We sort of have to define the DFA in such a way that all these paths collapse to one path. So for that, one way of doing it is the way that I'm going to describe. So we define a DFA where instead, so if so recall that the NFA N had Qn sigma delta n Sn Fn. Now we are going to take the DFA to be the following. The DFA will be built on 2 to the Qn. So it will, every state of the DFA is going to correspond to a subset of states of the NFA N. So in M, one state will correspond to a subset of states in N, the NFA N. Sigma remains the same. We are going to be defining what delta M, Sm, Fm is. So Sm will correspond to the subset Sn. So I had a set of start states in the NFA N. Now I'm just going to say, okay, create a new state that corresponds to this particular subset, and make that the start state of the DFA. This seems to be a simple like this seems to be a natural way of collapsing all the possible start states to one start state by just capturing the entire subset as one thing. What about the final state? The final state could be the states corresponding to subsets. So look at any subset of Q that has non-empty intersection with Fn. So if there is a subset that contains some final state, I will look at the corresponding state in M, the DFA M. I will say that state is a final state. So look at a state in the DFA M. Look at its corresponding subset. It's a subset of, it corresponds to a subset of Q by definition. If this subset contains a final state, then I will say that this particular state in the DFA M is a final state. And finally, the transition function delta M will be defined as follows. Look at the state corresponding to the subset A. So A is a subset of Q. Look at the state in the DFA M corresponding to the subset A. Suppose I read A, small a as the input alphabet, then this will be the single step. This will correspond to the state This will be the state corresponding to the set of states reachable from A by a single transition labeled with A. So delta M AA is equal to delta hat N AA. So delta hat N AA, please note that delta N was defined in such a way that the input parameters was a single state and a single alphabet. If I have to incorporate a subset of states as an input parameter, I have to go to delta hat N. That is why delta hat N, over here delta hat N has been used. Delta hat NAA basically means the set of states reachable from the set A uh, by outgoing edges labeled by A. The state in the DFA-M corresponding to this set of states is going to be the output state of delta M AA. Okay, so now we have the formal definitions. Now let's see what exactly is happening. So we'll do this with some lemmas. So let's look at a subset A of Q. Sorry, a subset A of 2 to the Q. No, sorry. Let's this statement is not completely correct. We are looking at a state A of 2 to the Q, and we know that A is a subset of the initial set of states Q of the NFA. So Q was the set of states, actually it is Qn. Qn was the set of states of the NFA N. A is a subset of Qn, and there is a state corresponding to A in the DFA M. Okay, and now look at a string X, then delta hat M AX is equal to delta hat N AX. So basically what we are saying is the multi-step function in the DFA will behave uh, in a natural way similar to the multi-step function of the NFA. Now that we are sort of collapsing subsets of states of the NFA to single states of the DFA, we should be able to talk about the multi-step extension of the DFA transition function uh, with respect to the multi-step extension of the NFA transition map. So the formal way of proving this is by induction on the length of input string X. In the base case, X is epsilon. So the left hand side becomes delta hat M A epsilon, which is equal to A, because if I am at a particular state, then I will remain in the same state. This is by definition of the transition function. If I am at a particular state A is a state in my DFA M. It is a subset of states of my NFA N, but it is a state, it corresponds to a state in my DFA M. So delta hat M A on reading the empty string or on not getting an input alphabet will remain in the same state A. And A is a and now how can we think of A in terms of delta hat N? Delta hat N for an input subset of states and on not reading any input alphabet will remain in the same subset of states, and therefore by definition it will be A. Therefore this statement is true for the base case. Now let's look at the inductive step. Suppose it's true for all x of a particular length, we will be trying to prove that the hypothesis extends to xa for any alphabet A. So the left hand side is delta hat M A xa. This, by definition of the transition function, of the multi-step transition function, is delta m, delta hat m, ax, a. Now, if we zoom into this, then we know that we have a smaller string x, so we can replace it by the right hand. We can apply induction hypothesis and replace this statement highlighted in this expression highlighted in purple by the right hand side of the claimed statement, and that is capital delta hat n ax. So this expression now becomes delta m of capital delta N hat AXA. Now again, by induction hypothesis on, so this is one more step. So delta m on application on a single on a string of length 1, we know behaves in the same way as delta. Oh, okay. So actually we can do induction hypothesis, or we can just use the definition. Over here, let's forget the induction hypothesis. We don't need induction hypothesis. Just by definition, delta m of a set of states, delta m of a state corresponding to a set of states. This corresponds to a set of states in Q, and therefore this is a state in the DFA M. So delta m for a state in M and a single alphabet A as input is defined as delta hat n of that set of states and A, and that set of states happens to be delta hat n ax. And now from the earlier lemma, we know that we can, if delta hat, in the earlier lemma, this was the right hand side. If I had a string xa, then I could also break it up into x and a, and delta hat n could be broken up. So this is the right hand side of the earlier lemma, and this is the left hand side. So they are equal. And therefore I have obtained the right hand side of the claimed statement for the string xa, and this was the left. I started with the left hand side of the claim statement for with the string xa, and therefore I have proven the induction step. So this statement that delta hat m ax is equal to capital delta hat n ax is true. So basically, the multi-step transition function is behaving in a very similar fashion as the multi-step transition map. Now let's come to the theorem, which states that the same set of strings is accepted by m and n. So why is this so? Suppose x belongs to the language accepted by m. So x is a string accepted by m, which basically means that delta hat m smx belongs to fm. So basically, if I started from the start state of the DFA m and I have x as the input string, I have reached a final state of the DFA. That is why x belongs to L of m. Now, this is same as saying that delta hat m smx has non-empty intersection with f of n. Now think of delta hat s of smx to be, so this is basically, this is a state in the DFA, which means it corresponds to a set of states in the NFA n, right? So that means delta hat m smx can be thought of as a set of states of Q, and by definition of Fm, the fact that delta hat m smx, the state delta hat m smx is a final state, by definition means that the set of states delta hat m smx of Q of Qn has a non-empty intersection with Fn. And then uh, this by the previous lemma we know that this set of states is same as this set of states is same as delta hat n Sn x. And what this statement is saying, it can be rewritten as delta hat n Sn x has non-empty intersection with Fn. And according to definition of Ln, this basically means that x belongs to Ln. So we had an NFA, uh, which was we had an NFA N, which was accepting the language Ln, and we showed that any x that is accepted by the DFA M is also belongs to L of n. It also belongs to the language of n. Now, please see that if you work upwards, the same. So if this was if and only if conditions instead of implies, the same thing holds. So actually, you can also show that if x belongs to L of n, the path can be traced backwards, right? You can show that if x belongs to L of n, it also belongs to L of m. And therefore, the same set of strings are going to be accepted by m and n. So DFAs and NFAs have the same power. That is, a language accepted by an NFA is also a regular set. If a language is being accepted by an NFA, we can construct a DFA accepting the same language. And we have seen a simple argument to show that any regular set can be accepted by an NFA. There is a simple construction of an NFA that will accept a regular set. So therefore, the non-determinism, although at first it seemed like we were giving a lot of power, actually it's not adding power to finite automata. NFAs and DFAs have the same power. So finally, I will come to a slightly more relaxed definition of finite automata, where we are allowing a little more freedom in the definition. Again, we will see that this does not increase the power of the finite automata. What we will do is we will allow transitions with label with label epsilon. Basically, we are trying to say that there are spontaneous transitions. We will allow transitions from one state to another state even when there is no input alphabet. So even when I'm reading a null string or an empty string, epsilon, I will be able to change from one state to another. So again, this seems like we are giving the finite automata much more power. Earlier we were saying, and in fact we saw in many places we argued that the definitions were built and the arguments were such that if you it was required that if you did not read any input alphabet, you stayed in the same set or same state or in the same set of states. But now we are adding more power. We are saying that we will be allowing transitions without reading any input alphabet. So it means so what it means is the automaton is making such a transition without reading an input alphabet. So an example of this is, suppose I want to find an automaton for x such that x is a subset, x is a string from a star, and x, the length of x is divisible by either 2 or 7. Okay, so either the length is divisible by 2 or by 7. So a priori it is not clear how to form a how to design a transition diagram for a DFA or an NFA that will accept this language, this given language. But it is very easy if I removed one of them, one of the conditions. If I said that x is divisible by 2, if I only said x is divisible by 2, then it is very easy to draw a DFA for this. I will have a start state. This will be my end state. This is my start state and this is my end state. And I have another state. Basically, it helps to count the number of A's I have encountered. So at the first state, when I am at an odd number A, then I will go to the I will go to the non-final state, and when I'm at an even count of A, then I will go to the final state. Uh, then I will transition to the final state. Similarly, if I just said x is divisible, length of x is divisible by 7, just condition 7, then this is a valid deterministic finite automata for that language. But how do I take the union of these two things? Of course, we know how to do it. We know the product construction, and we know how to build how to build a DFA for the union of two regular sets. But with the epsilon transition, this happens very quickly, right? You just add a new start state. You add a new start state, and you add epsilon transitions to the start states of the two DFAs. So you had two DFAs. Add forget the start states of the original start states of the two DFAs. Just add these two edges from the new start state, and label them as epsilon transitions. And this is a much this is a much more succinct finite automata for this language. Again, uh, I already mentioned that it is possible, at least for this language, it is possible to draw a DFA, because we know that x divisible by 2, there is a this the first purple the first purple part is basically a DFA for that language. Length of x divisible by 7, the second purple DFA, works for accepts that language. And we know, using product construction and De Morgan's law, we know how to construct a DFA for the union of these two regular sets. But if I added epsilon transition, the diagram becomes much smaller, and the number of steps also becomes much smaller. So at least for this example, epsilon transition is not adding power, it's just making the diagram better. So, but actually, does epsilon transition add power to finite automata? They do not add any power, and I would like you to try and prove this. So basically, I'll give you a hint. Um, if I am adding epsilon transitions, please try to see. So if I was reaching a state through epsilon, if I was reaching from one state to another state using paths that had epsilon transitions, in reality, what does that mean? In reality, what are the alphabets that that the machine is reading in order to reach that state? So what are the actual alphabets that are being read in order to reach that state? So now, can I replace this epsilon transition edge by a set of edges, or a set of states and edges which are labeled by actual alphabets? So please try to do this. Basically, the moral of the story is that epsilon transitions do not add power to finite automata. So even if even if I'm drawing a transition diagram for of a finite automata that allows epsilon transitions, that finite automata is still accepting a regular set. I can still find a DFA for the same set. I can still find an NFA for the same set. So DFAs have the same power as NFAs. They have the same power as NFAs that also allow epsilon transition. Now, in the final part, let's revisit the two closure properties on regular sets that we had left behind. One was concatenation of two regular sets, and the other was the star operation. So the first one, let's try to construct a DFA or NFA for AB where A and B are regular sets. So I know that uh, M1 is a DFA for A and M2 is a DFA for B. And I will try to construct an NFA with epsilon transitions for AB. Okay, and the idea is, so suppose I have L of M1, L of M1 is A, and suppose this is a schematic diagram of M1 where I have indicated the start state, the final states, and some non-final states. I do not give edges that correspond to the transitions. Again, I give another schematic diagram for M2, which is accepting B. Again, you have the start state and some information about final state and non-final states. One way of using these two, let's say I make a copy of M1 and I make a copy of M1 and I make a copy of M2, and now uh, for my new machine, for my new finite automata for AB, the start state will be the start state of M1. The end states will be the end states of M2. And now from the original end states of M1, I will put epsilon transitions to the original start state of M2. So basically what this is saying is, I start from the start state of finite automata accepting A. If I get a string from A, suppose I get a string, the first part of my input string is a string from A, let's call it X, then it is going to reach some final state in M1. Because M1 was a finite automata accepting A, the path which is labeled by X is going to start from the start state and end at some original end state of M1. Now I make a spontaneous or an epsilon transition to the start state of M2, as if from M1, without reading anything new, as if I have already moved to simulating M2. Now, let's say the rest of the input string was Y and Y belonged to B. Then, if I'm simulating, now I'm simulating inside M2, and therefore, if Y belong to B, I will be ending up at a end state of M2. And therefore, if my input string was X concatenated with Y, where X was coming from A and Y was coming from B, then I'm actually accepting X and Y, which belongs to A concatenated with B. So this is how we define an NFA with epsilon transition for AB. And since an NFA with epsilon transition does not add power to the finite automata, we know that AB is also a regular set. So uh, regular sets are closed under concatenation. And the last thing that we will see is closure under the star operator. So if A is regular, then so is A star. How do we do it? So if A is regular, then let's say M is the machine, is a finite automata. You can think of it as a DFA for A. Because A is regular, I know that there is a DFA for A. Let M be that DFA. So now I take a copy of M, and now I will try to convert it into a finite automata. So basically it will be um, um, an NFA with epsilon transition, which will be accepting A star. So what do I do? The construction is as follows. You create a new start state. So I create a new start state, and I put an epsilon transition from the new start state to the old start state. And I create and look at the old final states. I put epsilon transitions from the old final states to the new start state. And finally, I make the new start state the final state. Okay, so my new start state is my final state. I make epsilon transition from the new start state to the uh, to the um, uh, to, to the old start state, and I make epsilon transitions from the final state to the new start state. And also one last thing is I make an epsilon transition, epsilon loop in the new start state. So this is an epsilon. This is an epsilon loop at the new start state. Okay, so then what is happening? First of all, this epsilon loop is ensuring that epsilon, the empty string epsilon, is being accepted. Empty string epsilon belongs to A star and therefore it should be accepted. Now for everything else. So what are the strings of A star? Basically, you have, you can have multiple concatenations of strings from A. Right? A star is defined as by strings. You take multiple strings from A and concatenate them. And this is exactly what is happening. From the new start state, you make a spontaneous transition to the old start state, and then you start reading the input. You start reading the input. At some point, suppose you have read x1. So let's say the input string is x1, x2, x3, where x1, x2, x3 all belong to A, and x1, x2, x3, the concatenated version belongs to A star. So you read x1, you reach some final state, then make an epsilon transition back to the new start state, make an epsilon transition to the old start state, again start a path. In some way you reach another final state after reading x2, come back via the epsilon transition to the new start state, again use the epsilon transition to the old start state, then take another path labeled x3. It will end up in a final state of the copy of M. Then the final part is use the epsilon transition from this final state, from this original final state to the new start state, which is the final state of this new finite automata. So the new start state is also the new final state. And what we see is x1, if x1 and x2 and x3 belong to A, then the concatenation x1, x2, x3 is going to be accepted by this new finite automata. And this is an NFA which allows epsilon transitions. So using like these simple constructions now, after allowing epsilon transitions on NFAs, we can show that regular sets are closed under concatenation as well as the star operation. So this brings us to the end of this lecture. We will continue with finite automata in the next lecture. Thank you.